Okay, so let's get started with the video on electric potential. Before we do, we're going to kind of talk about gravity a bit and what we could do with that, and then transition that as like a parallel into what we're going to do here with electric. Right, so let's say you have some staircase where each step is 1 meter. And you have a 2 kilogram box. Just to make life easy, we're going to say G is 10 meters per second squared, just so we don't have to deal with any weird numbers. And let's say you wanted to figure out the potential energy required to move this box up 1 step. Well, that would just be U sub G is equal to mgh is equal to 2 times 10 times 1 joules gives us 20 joules. All right, let's say you wanted to go to the second step. That would just be U is equal to mgh is 2 times 10 times 2 joules, which will give us 40 joules. And so if we wanted to, we could go for each of these steps and write down how much energy was required to be on each step. But this is only true if m is equal to 2 kilograms. So what would we do if we had a different mass? Right, then none of these values would be correct anymore. So what we do is we figure out the amount of energy required to do this with 1 kilogram, and then we have some value we can multiply by whatever mass we then later have to get the correct answer. And so we would have 10 joules, 20 joules, 30 joules for 1, 2, and 3 meters for 1 kilogram if G is 10. And so you can have this maybe rewritten as 30 joules per kilogram, right? Or 20 joules per kilogram, or 10 joules per kilogram. So now you have some kind of a value that can be multiplied by any mass to figure out the gravitational potential energy, right? And so that's much more interesting of a quantity than the actual potential energy, because now this is general and it'll apply to whatever mass you bring in. And so we want to do something very similar for electric potential energy, right? And so, for electric potential energy, if you wanted to find the amount of energy per charge, you would just call that potential, and that's going to have units of joules per coulomb, right? And so that's going to be the energy per charge. And that's what electric potential is. So before we dive into that, we're going to just briefly review potential energy. All right, and so before we start talking about that, let's talk about kinetic energy. Right, we could have K is equal to 1/2 mv squared. And this would be the total energy for a particle subject to no forces. Right. And so if you have a particle that's just kind of hanging out in free space, there's no gravity, no electric forces, nothing like that to act on, no springs to compress or anything, then its total energy is its kinetic energy. Right. And we know that we can have a delta K equal to K final minus K initial. And so we can say delta K is less than 0 if a particle slows down. And we can say delta K is greater than 0 if a particle speeds up. Right. And so one thing to keep in mind is that a single particle can have no potential energy. Right? It has to interact with something. Must interact with another particle or force. Right, and so just like if you had a block of mass completely isolated in a system of its own, it doesn't have any gravitational potential energy, you need to maybe have the mass of the Earth or something to exert a force on it. Right? So true is if you had a positive charge somewhere, right, and there's nothing else, right, in that system, it doesn't matter if it's over here or down here or over here, right? It can go anywhere and there's no difference, right? There is no potential energy. Right, and so the mass in the Earth would have an associated potential energy, and then that's how we get there. And so if a single charge cannot have an electrostatic potential energy, there must be an interaction between two charges at least to have potential energy. Okay. Right. And so the idea there is something that you must have one charge to make an electric field that now if you have your other charge there, right, could be negative, could be positive, now it can interact with that field and have some associated potential energy. Cool. And so let's talk about if we have a single particle system, if you have a change in kinetic energy for that system, that has to be done by the work of the surroundings. Right? So currently, if there's just one charge that's not interacting with any others, in order to change its velocity, something in the surroundings has to exert a force on it, and so it has to do work on it in that way. And so let's go ahead and box this equation, because this is for the single particle system. And then just quickly, we'll do a reminder of what work is. It's a scalar quantity equal to F dot D, or we could do F dot delta L, where we could have delta L is equal to sum delta L x I hat plus delta L y j hat plus some delta L z k hat. All right. And then just a quick reminder about dot products. If you have some vector A dotted with some vector B, that is equal to A and B, the magnitude multiplied together, times cosine theta, where theta is the angle between them. Right, and so if we have work is equal to F dot delta L, we can say that's equal to Fx delta Lx plus Fy delta Ly plus Fz delta Lz. Right, and you could have kept this as a d and had it be a dx, a dy, a dz, but this is what we're going to stick with for now. And so as kind of discussed briefly, potential energy is associated with pairs of interacting objects. And so if we had a system, we'll say for a system, containing a pair of particles the kinetic energy of the system can only be changed by changes in the potential energy of the particles or external work. That says of, not or. Right. And so when we say changes of the potential energy of the particles, we can go ahead and say that's equal to the negative internal work. And so we can say delta K system minus the internal work has to be equal to the work surrounding, right? As a conservation of energy statement. And so then we also said that delta U is equal to the negative of the internal work, right? And so it would have to be the negative, because if we increase in potential energy, if that is greater than 0, then we typically need delta K to be less than 0, which implies negative work, right? Because work energy theorem tells us the change in kinetic energy is equal to the work done. Okay. And so we have this nice equation to define the change in potential energy or the internal work done. And so let's look at a system of charged objects. And so let's start with a system that has no external forces. And so we could say delta K system plus delta U in the system is equal to 0, right? So 0 work is done by the surroundings, right? And so for the first thing we want to look at, let's consider some parallel plate capacitor. So we'll have an electric field that points from positive to negative. And that should do it. And then let's go ahead and put a proton in there. And so we'll call this little P plus, and that's this guy right here. And so let's say initially K is equal to 0, and we let this go. Let's see. So it's going to have a force pulling it this way, right? It's going to get pulled towards the negative plate. And so if it has some force greater than 0, there's an acceleration that's greater than 0, and then delta K is greater than 0. Right? If we're speeding up, we're increasing in kinetic energy, and so we would have a kinetic energy greater than 0, which would imply a change in potential energy is less than 0. And if we wanted to take a look at that, we could say delta U, and just as a reminder, that's the negative of the internal work done, is going to be negative f of x delta Lx plus Fy delta Ly plus Fz delta Lz. Okay, and we have the negative here because we are traveling in a direction. Wait, why do we have a negative there real quick? Oh, just because it's the negative of the work, right? So we have the negative of the work, gives us delta U, and so we have a minus sign out there for that reason. Cool, thought I was going crazy for a second. And we know F is equal to QE, right? That's one of our equations we got. And so if we want to rewrite this again, we can say it's equal to negative E, right? The elemental charge, E sub x. That'll give us F in x. And then delta Lx plus E sub y, which is the force in y, times delta Ly plus E sub z, right? The force in z, delta Lz. And if we look at this, well, we can say a couple things. E sub y is 0, just based on our coordinate system, what we drew. And also delta y is 0, E sub z, that's all 0. And so we're just going to go ahead and get rid of those. And we get delta U is equal to negative the elemental charge times whatever the electric field in x was, times delta Lx. All right, and so that would be the change in potential energy. All right, and so let's craft up another situation here, where maybe we start with kinetic energy and we're going to turn that into potential. And so let's say we have a very similar setup. Okay. Oh no. There we go. That way there's four of each. You know, everything's good. We're happy. And so again, the electric field's going to go this way. And this time, let's go ahead and say we have a... Well, let's see. What color do we want? Let's do green for an electron. And so let's say we have an electron coming in from this side. And let's say it has some initial velocity, so therefore has some kinetic energy. And then let's say this electron's going to kind of zip into here up to, I don't know, we'll call this point B. And then let's say it turns around and starts heading back this way. All right, because it comes in with some kinetic energy, right? Negative charges want to move against the electric field. You can also see it's going towards the negative side, which is going to repel it. And so it's going to kind of have the brakes on it until it gets to this point B out here, where it'll turn around and head back to the other plate. And so we can say for this whole journey, delta U was greater than 0, right? Because we're starting off with no potential energy, and then as we go this distance, we're increasing potential energy, right? And so we'll say we're only going to look for the leg of the journey for where it goes towards B, right? And so it's losing potential energy, or it's gaining potential energy, and so therefore it must be losing kinetic energy, what you would expect if it's going to come in and come to a stop before turning around. And so we can do something similar where we look for delta U is equal to negative, we'll call this F sub x delta Lx. And then we're just going to say we know the other two are 0, right? No need to write that all out again. So we can say that's negative. And what's the force going to be? Q, E sub x delta Lx. All right, we have a negative times a negative, and so we get delta U is equal to E sub x delta Lx. All right, and so there we go. I'm going to put boxes around these because I think they're about to be interesting in a second. Okay, and so let's briefly talk about potential difference in a uniform field. All right, and so far we haven't even really talked about what the electric potential is, right? We've just been talking about potential energies. So let's go ahead and figure that out. Let's kind of think out loud for a second. So when working with forces, it was pretty useful to calculate the electric field I'll go ahead and say you're a vector still, why not? Because this enabled us to, well, let's say. So it's useful to find the electric field in a location without having to worry about what kind of charge or charged particle, we'll say, might come along. Right? And so, we had the, if you have F2, you could say is Q2 times E1, right? So if you have the electric field for some random particle, particle 1, if you multiply that by the other particle's charge, you get the force on that other particle, right? And so that was really useful because if you had E1, then you could solve F2 for any Q2 that happened to come along. And so let's say we want something that kind of follows delta U is going to be Q times that something, right? And so that way we could find the change in potential energy for any given particle that shows up, right? And so let's take a look at what we had up here for, this was for the proton, and this was for the electron. And so we had, for the proton, delta U was equal to negative E sub x delta Lx, and that's not an E. And for the electron, we had delta U was negative E sub x delta L sub x. Right? And so in both cases, we have this negative E sub x, well, we'll just say delta x, right? And that's what we're going to define to be delta V. Okay? And so we can go ahead, right, and we're going to say that because in both cases, that's what you multiplied the total charge applied to, right? And so when you had the proton, you just had an E in there. For the electron, you had the negative E. And so both cases, you have that minus sign out front, so that's why we're hanging on to that. And so we can say delta U is equal to Q delta V. That's not the best way. There we go. Nice sharp angle, so it's definitely not a U. And if that's true, then we can say delta V is equal to delta U over Q. And we can define the units for delta V, our potential difference. Has units. Shocker, right? 1 volt is going to be 1 joule per coulomb. Okay. Let's see. I'm gonna box these just because they're the important equation. Yeah, this one. Yeah, give it a box too. Why not? Have a great day. And so this is a bit of an aside, but we can also, if we're talking about energy, you can have the electron volt, which is just equal to, our 1.602 times 10 to the 19th coulombs times 1 volt, right, which we have here, is 1 joule per coulomb. Oh, wow. Would you look at that? Those cancel out. And we get it's equal to 1.602 times 10 to the negative 19 joules. And that's just the definition of an electron volt. That's something you'll probably see around. Cool. So let's keep on cruising and say what if the path isn't parallel to the electric field, which we're going to make sure we say is still uniform for now. Right. And so it was parallel, so we got to go ahead and say, these are all 0. Right, these were all 0. And so now we don't have that luxury. But, we'll be okay. We would say delta V is negative E sub x delta x plus E sub y delta y plus E sub z delta z. Or you could say delta V is equal to the negative E dot delta L, right? Which we could rewrite as, in some kind of vector notation, E sub x, E sub y, E sub z, dot that with delta x, delta y, and delta z. Right, and so both of these are true for E is constant, right, for uniform electric fields. And so if we can find the potential from the electric field, it would stand to reason that we can also find the electric field from the potential difference. Okay, and so all we do is rearrange our equation a little bit, and we would get E sub x is equal to the negative delta V over delta x. All right, because remember we had delta V is negative E dot delta x. All right, and so we just divided both sides by, I guess, a negative delta x, and we're having a good time. Okay, but we could also say e sub x is equal to the negative of the limit that delta x goes to 0 of delta v over delta x. We want some instantaneous electric field. And so that's negative dv dx. And again, we can do this in other dimensions. And so we get e sub x is negative dv dx. E sub y is equal to negative dv dy. E sub z, you guessed it, negative dv dz, which is known as taking a gradient. Well, we'll get there in a second. And so technically, it should be partial derivatives. And so we get e sub x is negative dv dx, e sub y dv dy, e sub z dv dz, or we can rewrite this as e is equal to the negative gradient, oh, nope, not a dot product, scalar, of potential, right? And so we would say the electric field is the gradient of potential. Right, and so anytime you multiply by the del operator there, that's called the gradient when you do it to a scalar. And so just to make sure everyone's on the same page, we have this is that operator. Okay. All right, let's put the box around this equation because that's just a beauty right there. And let's briefly talk about the sign of potential. And so if the path is going in the direction of E, then we have delta V is less than 0. If we have path going opposite direction of E, then we would have delta V is greater than 0. Right, and so it should kind of make some sense, right? If, right, let's say you have a positive charge and you have your E field going this way, right? As that goes this way, right, it's going to lower potential energy you've dropped in potential, right? And we'll not think about the negative charge just yet. Right, and then if we have the path is perpendicular to E, then we just get delta V is equal to 0. And so just a quick, I guess, little notational thing. If you ever have delta V is VB minus VA, that means you started at some point A and went to some point B. If you have delta V is VA minus VB, you start at some point B and you went to some point A. Just something to keep in mind. And so let's talk about a non-uniform field here. Okay, and so let's say we have two adjacent regions with different fields. All right, I don't know if everyone's seen this before. That just means with. This would be without. Learn something new every day, hopefully. Okay, and so let's say we have maybe some plate here that's all positive charges. Plate over here, we'll have that also be positive charges. And let's say there's a plate in the middle. It's negative charges. And so we could define E1 going this way, E2 going this way. And let's say we have, I don't know, what do we have? A positive particle, say it's a proton. Okay, let's do this as blue. And so that's a proton. And we will say it starts out at some point A. And it's going to go to some point B. All right. Where we can say this has some location XA 0, 0. And this is maybe XB 0, 0. Because we just have reliable. All right, so let's straighten this guy up. He's going down at a wonky angle. All right, there we go. Now we all feel better. Okay, so in order to evaluate this, I'm going to go ahead and come in and make some point C, right? And then I'm going to define delta V1 is equal to negative E1x times xc minus xa. All right, and so that's just the potential difference going from here to here. And then we'll have delta V2 is going to be negative E2x. And then that'll be xb minus xc, and that'll correspond to the potential difference from this hop right here. Okay, and so we can say delta v is equal to delta v1 plus delta v2, which we can say is negative e1x times xc minus xa minus e2x times xb minus xc. Or we could rewrite this as delta v is equal to the sum, all right, over some index. So we'll say, goes to n, I guess. That doesn't super matter. And so we'll say negative e sub I x delta x sub I. Right, and that would be good for just x. But let's go ahead and do everything. All right, and so if you have like many legs of your journey, you can go ahead and sum up the total potential difference. Or if we wanted to rewrite this in a bit more succinct, we could say delta v is equal to the negative sum of just E dot dl. All right, and so for however many you have. Okay, and so, those of you who are getting used to this game should go, okay, we dealt with one thing, now we have the sum of things. And so what are we probably going to do in a few minutes, right? go to a distribution of things that we're going to have to integrate. But let's not get too carried away here. So let's talk about a conductor real quick. A conductor in equilibrium. Okay. And so we can say, let's say you move just in a conductor. And you would have delta V is equal to negative E sub x delta x plus E sub y delta y plus E sub z delta z. But what do we know about electric fields in a conductor? 0. Okay. And so if this is equal to 0, right, if delta V is equal to 0, we can say inside a conductor, the potential is a constant. All right, that's true for inside a conductor. Okay, and so now let's talk about the potential difference in a region of varying E field. Okay, and so what you're going to want to do there, step 1, choose a path. And divide it into pieces. Just like we did up here, right? We took this path and we just split it in half. And so we'll divide it into pieces and we'll call those each a delta L, or maybe delta L sub I if you want. And then you want to write delta V is equal to negative E dot, well, let's say E sub I, D sub L I for each piece. And then add all contributions. And so this whole process here, this just smells like integration. All right, y'all smell that? That's integration in the air. All right, and so if we want, we can say delta V is equal to the negative integral from some initial to some final point of E dot dl. And we will note that this is path independent, but we'll put a box around that. Okay, so I'm going to end this video here. We'll finish the second half of potential, as soon as I can get to it. In the event I splice the two videos together, this would be a great time to pause, take a break, go get some snacks. I don't know, whatever it is y'all do.